Hi, everybody. My name is Robert Schimkowitsch. I work on control center systems for hydroelectric power plants with 25 years of experience, 15 with C++ and Qt, mostly in the desktop and UI space. Lately, I do refine requirements, do a little architecture, code design, and generally try to make our junior team members more productive. I love working with people, which is why I also co-founded the C++ user group Vienna. If you ever come there, please join us at one of our events, no matter whether you want to watch a talk or give a talk or just have a drink with us. Over the time, I have solved similar problems more than once, and this has given me an appreciation of how my own coding style changed over time. So when I look at all the code now, my instinct is to ask, how would I write this today? So imagine you are me, and you have just stumbled over this piece of older code. Now, I'm not looking for an in-depth analysis here. Just give me your gut feeling. Who likes this kind of code? I see no hands. And who does not like this kind of code? I see quite a few hands. I don't like it, and I'll tell you why. It mixes the core logic of the function with error handling, making it really hard to see at a glance what the function does. In addition, we have this funny return type, which is actually just a success flag. It tells us whether the function succeeded. The real return value is hidden at the end of the parameter chain. We're not going to mix those two up, are we? Use exceptions, and you could have something like this. Except you have to throw somewhere up the call stack, you have to catch somewhere down the call stack, and if you forget to catch, you crash. And also, should we use exceptions for domain errors? There's some discussion around that. So maybe you can't or you don't want to use exceptions, at least for this piece of code. So what else could we do? We like classes, right? So why not make the error flag a class member? So now every function can read and write there. Looks promising, right? But we have just moved the checks around. We have not really solved anything. And congratulations, we have created our own little dependency hell. Everything now depends on that single error flag. And this is called shared mutable state, and it's poison to local reasoning and thread safety. So let's take one step back and look at the return type issue first. We can combine the success flag with the actual output into an optional of the return value type. That way there's no ambiguity anymore. If the optional is empty, that implies failure, and if it holds a value, we can use it. And then we throw away all our if statements and let that optional do the work for us. This way, the sequence is clear and plain to see. And optional does the error handling for us, we cannot forget about it. This is a monadic operation in action. I've set myself 3 goals for this talk. The first goal is that after the talk, you understand what functors and monads do, not what they are. I'm focusing on practical usability rather than theory. The second is that you are able to write code using the monadic operations in the standard library without much trouble, and that includes knowing how to pass callables and avoid some of the traps there are. And I also want to give you enough leads and references that, should you choose to do so, you can dig further into the topic. Yeah, the code that you see on the slides is slideware code. There is a GitHub repository. The link is already on the Discord, and I will post it at the end of the presentation on the slide. You find everything there: code, slides, further references, benchmarks, whatever you want. And I would much prefer to take questions at the end of the session. So maybe note the slide number, because I have quite a bit of material to get through, and I want to give you a complete picture. And maybe I'll answer the question 3 slides later anyway. And did I mention I have kids? I was able to get rid of the dinosaurs, but there might be some unicorns still hiding in these slides. Okay, I promised monads, now I talk about functors. What's this? Now, functors are kind of the foundation of monads. They don't have all the properties of a monad, but every monad is a functor. So now say, yeah, I know what a functor is. It's this thing with the call operator. And you are not wrong. This term is used, so fine. But this is not the functor we're looking for. So what are we looking for? Let's tell a little story. Once upon a time, there was a little sequence of code, and it consisted only of two functions. One, to calculate the area of a circle based on the radius, and the second one, to format an area nicely into a string. They were combined, so you could pass a radius and get a nicely formatted string of the circle's area, and everything was good. But then a developer came and she brought a vector of radii and wanted a vector of strings naturally. No problem, they said, we will just make a loop. And inside the loop, we will do much like before. But then one of the functions said, this does not feel right. I'm sitting here together with code that knows nothing about area or radius. It has nothing to do with me. I feel we have violated the single responsibility principle. And when I asked the C what he sees in the future, he said, code duplication. How much better would it be if somebody could transform us poor functions so we can handle vectors? Like maybe we create a new function that takes the old function as an argument. Now, the new function would accept the vector of whatever parameter type the old function accepted, and would return a vector of whatever parameter type the old function returned. So for format area, which accepts a double and returns a string, the new function would accept a vector of double and return a vector of string. Then we can combine those two new functions and they can natively handle vectors. The vector aspect is implemented only once and separated out nicely. This is one way to apply a functor. But there is a different way that's sometimes more useful in practice. Let's think about a functor as a container or a magic box. Put in a vector of building materials, send in a worker, just a single worker with a plan, and take out a vector of houses. This functor is a class that holds the value we want to transform in the next step as a class member. And it has a member function called transform, typically, that accepts a function which takes a single argument and can transform it. And now the wrapper applies it to the whole vector. Yeah. We pass in the function, we apply it to all items, we return a new functor with the new values, and we can repeat the process in liberty as long as we want. Again, the vector part is implemented separately, once nicely separated. Both are functors, both solve our problem. Let's take a step back again and look what really goes on. We start with the radius, we can calculate the area, and we can format the area, we get a string. Awesome. Now on the vector side of things, we can construct a vector from a single or multiple radii. We could do the same for area and string, but that's not what we're interested in right now. We want to start with the vector of radii. And we have this function which can transform the single item. And now we use functor magic to apply this function to all items, so we get a vector of areas. And then we can do the same to go from areas to strings. The nice thing about it is we are not bound by vector. Our functions stay the same, and we can apply the same using a different functor with optional instead of vector. For example, it could be other things as well. So we have separated two things really nicely. Now let's add a little theory. There are two rules that functors have to follow. And the first rule is the rule of composition. Because we could compose our two separate functions into one function, and we could apply that on our functor, and it should give us a vector of strings. And it must be the exact same vector of strings as if we had applied it stage by stage in the pipeline. The second rule is the rule of identity. Identity needs to be preserved. What does that mean? This time, we use a different function, split identity, which accepts an argument and returns it unchanged. Sounds a little silly if we have not used it, but please play along. So we can apply this function, and it needs to come to the exact same result as the initial input. This is important because it means the functor cannot use any other state, internal or external, to influence the result. It can only use the function that you passed it. So you have this guarantee. So in summary, functors provide you a mapping, for example, from single values to containers or to optionals or to other things. And this mapping needs to preserve composition and identity. We've seen that functors can be implemented in different ways. They don't have to be objects. They don't have to hold values. Some of those that we will see hold values, some don't. Both are functors. Now I have used vector as an example to show the benefits of using a functor. But of course, you don't always want to use vector. You might want to use a different container or any range. And you also don't want to write the functor yourself. You don't have to. There's split ranges views. When we look back at the vector example, at the classic implementation, we can get pretty much the same. So same result, same output, that's for sure, using this piece of code. So let's decompose that. Split ranges views gives us a function called transform, which takes two arguments. The first one is the input values that I start from, and the second one is a callable, a function that I want to apply to all the items in that range. The output is a new range, which I immediately can use as input to the next transform. Now, this inner-outer transform notation is pretty awkward and gets downright confusing if you get longer pipelines. So the pipe operator to the rescue. This way you get a clean and nice notation. And I guess most of us are used to it somewhere, bash or shell, whatever. And I think it expresses the intent more nicely. So how does that work? We start with our input. It basically, of course not literally, injects the input as a hidden first parameter into the transform. And then the transform creates a new range, and this becomes the input for the next stage of the pipeline. But there are two questions here. What do we actually return from that function? And what type is the output? Because the type output is not a container, it does not hold values. Think of it not as cake, but as a recipe to get cake. You know what to do? You just need the ingredients. And that's the second part. Views typically don't own the data they use. Some do, but assume for now that they don't own the data, so you have to worry about lifetimes. Another thing about views is they are lazy. So they will only start evaluating once you start drawing data out of them. Constructing a view does not very much, almost nothing. So what type is the output now? Something like this, and it varies by compiler. So auto is pretty much the only way to make use of that. And that has implications. It means that you cannot really separate declaration from definition into different files. I mean, yeah, corner cases, but you should not. Still, it's not a template function because the return type is actually well known. We're just too lazy to type it. And when we start using such a function for multiple translation units, we will run into trouble. So what do you need to do? Mark such functions inline. Don't overuse them. Keep the scope where you use them within your visibility, so you also have a view on the lifetime of the underlying data. The alternative is to return a container. And C++23 gives us a nice facility for that, split ranges 2, which converts a range to a container of our choice. Can be standard library, can be third-party library, as long as the interface that's required exists. And this way we get a nice clean API. We can separate declaration from definition again. However, we lose the laziness because the values have to be computed at that point, and we will probably allocate memory. So in summary, views are more like a recipe, not like the cake. If somebody steals your ingredients, that's undefined behavior, and you don't get cake. They typically do not own the data, so be careful about that. Auto is the way to use them, and they evaluate lazily. And there are traps. Of course there are at C++. Depending on your compiler, build settings, and so on, this may crash, output garbage, or maybe even work. Let's walk through it quickly. We have a simple struct called cEntry. It has 2 integers and 1 string. And we have a function called getNearestEntry, which accepts an integer and returns a cEntry by value. And the implementation does not really matter here. Now, what I want, I have a vector of integers, and I want to create a view of cEntries based on that vector. But finally, I just want to print out the string member. So I grab the string member in a second transform. And then I print it somehow. So where's the bug? And maybe you can even see it. Okay, so what's going on? The first transformation uses getNearestEntry, which returns a cEntry by value. Second transformation gets mtext, which gives you a reference to mtext, but the cEntries are temporary. We are sitting there with a dangling reference. It's a bit like a function like this. You input an argument by value, and you pass out a reference to one of its members. That's equivalent, but it's maybe harder to see in the pipeline, so always use sanitizers. Passing callables is important, as you might have noticed, because both functors and monads need them to work. And when I started using this coding style, I sometimes had difficulty finding the right ways to pass my functions. And sometimes I just threw up my hands in despair and went back to classic coding. I'd like to spare you a lot of that trouble and show you some convenient ways to pass your functions. And an easy one is the free function. As long as there are no overloads, you can just pass it, and that's great. We will come to overloads later. Static functions of classes work pretty much the same way. You just need the class name for qualification. And then there's inline lambdas. You code what you need, where you need it, which is great if the code is very simple and short, and if you don't intend to reuse it elsewhere. One use case of inline lambdas is if you have overloads for free functions or something like that, wrapping it in a lambda helps the compiler pick the correct overload. One of the typical issues you have a function with multiple parameters, and the functor or monad will only provide one of them. Well, you can pass the rest via the lambda capture list. Similarly, if you want to call a member function of an object instance, for example, the functor passes you the object instance, you can have a lambda that will call the desired member function on it. There are other ways, but there's not enough time to cover all of them. Alternatively, if the functor gives you a value and you want to apply it to a member function of a known object instance, you can do that as well. And if you want to give a lambda name for documentation purposes or want to reuse it in multiple places, that's how you can do that. And there are also function objects which work pretty much like lambdas, give you a little more flexibility, and they are objects with the call operator. Sometimes it's nice to be able to inject behavior from the outside to give you, the user of your function, the ability to pass in a function that will be called at stage 3 of your pipeline, for example. And you can use step function for that. It wraps any callable. And the template arguments are the return type and the parameter types. And that way, you can allow your user to customize your algorithm. You can, of course, also do it with template parameters. And if you want to check if what you get passed is really a function of the correct signature or a callable of the correct signature, you can do that using the std invocable concept. Now, typically, you have templates will typically have better runtime characteristics, but add some complexities to your code. It's a trade-off you have to decide. To summarize, lambdas are a very flexible way, and they give you lots of ways to pass callables. The Swiss Army knife, I would say, and adds std function to inject behavior, and you have a good basic set to get started. Now that we heard about functors, we can talk about monads. As I mentioned, monads have all the properties of functors, plus something more. But let's start again with an example on how the monad solves a problem. Let's say we have a tree-like structure, and it consists of nodes. And a node has a function called getChildren, and it's not important how that exactly works. Important is we can have multiple children, so I return a vector of nodes. Now, when I want to call getChildren again, that doesn't work because it's not equipped to handle a vector of inputs. Let's see if functors can help us with that. So we start again with our vector of nodes as input. And then we transform it and we get a vector of nodes. Okay, the next transform is not going to be happy about that. So what do? We invoke monad magic and join the vectors or flatten them. So we make from a vector, we just make one vector. This unwraps one level of nesting. And that's the property of a monad. Then we can continue and do the transform again and do the join again. So in summary, and for our practical purposes here, theorists would shoot me, I know. A monad is a functor with the ability to unwrap a level of nesting. I know this is very hand-wavy, but I want to focus on the practical side of things. You typically cannot unwrap the last level of nesting. Monads are functors, so the rules of composition and identity still apply. And you will find that the functions for transform and join are often combined into functions that differ by name depending on which implementation you use. We will see a couple of examples. But let's now leave theory behind and look at examples. It has been said that a compiler is a tool that takes files as the input and returns diagnostics as output. Let's forget that it might also produce some usable object files and focus on the diagnostics, right? So in classic coding, I would have a function that prints a single diagnostic. Then I would have a function compile, which takes a file and gives me, of course, a vector of diagnostics. I don't expect just one. And then we can compile multiple files, and I say, okay, I have a project, whatever that means, which consists of multiple files, and I can get all the files in a project. And this would be a classic way to implement it in loop style. So we loop the projects, we get all the files in one project, we loop those files, we get the diagnostics of a single file, we loop those diagnostics, and we print them. Who has code such as this? Okay, yeah, third of the room maybe. Okay, how would we do that in a more monadic way using std ranges use? So we start here with our projects, and then we transform them into files. Now we have a vector of files, so we join that, giving us just a vector of files. Now we can compile. Again, we get a vector of diagnostics, so we join again, giving us just a vector of diagnostics, and then we can loop the diagnostics and print them. Here are both versions side by side. What do you think? Which one makes the intentions of the author clearer? Now, do they behave differently? In effect, no, they call the same functions in the same order with the same same arguments. There might be performance implications, but I'll come to that towards the end. Okay, I'd like to sidestep a little and talk about using functors and monads, and specifically ranges views, safely. And for me, pure functions are a key to that. Who knows what a pure function is? Okay, maybe a fourth of the room. Okay, for the others, I'll explain in a couple of minutes, but let's look at an example first. Here we start at the bottom with a vector of numbers. And what we want is to get a view of those numbers multiplied by 2. And so we use a function that returns such a view. And the function is above. Get multiplied view takes an input range and a multiplier and returns a new view which contains what I want. And inside the function, I have a helper lambda, which I will use for a single item, to multiply a single item. And the multiplier gets passed by the lambda capture. Then I return a view using that lambda. And down in my calling code, I can print. So what do we have? We have 2, 4, and 6 times 2. That's, of course, 4, 8, and 12. No, wait. OK, that doesn't look right. So what's going on here? So first, we pass the multiplier by value. OK, I guess that's fine. Then we capture it by reference. Oh, that looks a bit fishy, but it should actually still work. Ah, the view is lazy. So it will call the lambda after we have already left function scope. And we are sitting with a dangling reference to the multiplier. This was an example for split ranges views, but in general, when you use functors and monads, you need to be aware that they control when you get called, how often you get called, and in what context you get called. So how can you avoid bad usage of your functions? And I see mainly 2 choices. You can start a define print of the functor monad of your choice and see what guarantees it gives you. Or you can make your functions more robust by making them purer. And I'd like to explore that option. Now, what is a pure function? It has 2 properties. First, it will give you the same result for the same input, always, no questions asked. And it has no side effects. Let's look what that means in detail. So let's say we have a function that has some input and an output. If you had infinite memory, could you replace it by a lookup table? And if the answer is yes, then you're good on the first requirement. The second one is, what does no side effect means? Side effects mean, it means you're not writing to memory outside your own functions stack. You're not triggering other side effects such as external I/O. That's what no side effects mean. Pure functions have a lot of advantages. They're easy to reason about. You only need to inspect that function to understand what it does and how it works. It's easy to write unit tests for them. You can look at the function isolation. You can use the lookup table approach, a piece of the lookup table to check if the function really returns what you expect. And if it's really pure, it inherently is thread safe. Pure functions are useful in combination with functors and monads, but they are also very useful on their own. For example, I have a big function that interleaves complex logic with side effects. This function will typically be really hard to test. What I like to do is I separate it out into pure logic part that has as much of the complexity as possible and into much simpler side effecty execution part. And then I may add a wrapper so that for the outside user it looks like one function, but now I can test them separately. And testing the pure function is easier. I can use the lookup table approach, but even testing the execute function is typically easier because I can trigger the side effects I want to test specifically in a much simpler fashion. Now let's have a little quiz. I'll list some functions from the standard library and you tell me whether they are pure or not. Let's start with split max of integer with no custom comparison. Who thinks this is pure? Lots of hands. Who thinks this is not pure? This is pure, yes. Std fill, the function used to fill containers or ranges. Who thinks this is pure? A few hands. Who thinks this is not pure? A few more hands. Yeah, it writes to outside memory, so it's not pure. Std chrono system clock now. Who thinks this is pure? 1, 2 hands. Who thinks this is not pure? A lot more hands. Yeah, how would you write the lookup table for that? Then std sin, sinus with double, calculating the sinus. Who thinks this is pure? Who thinks this is not pure? Yeah, depending on your implementation, because it actually says that it uses global rounding modes, so it's using outside state. Then std ups absolute of integer, calculating the absolute value. Who thinks this is pure? Most. Who thinks this is not pure? Well, this is tricky because what do we do with int min? It's undefined behavior. Can we say this is pure? For me, this is a gray area. Then last, std any of, checking if a predicate holds true for any item in a range. Who thinks this is pure? Who thinks this is not pure? Well, this one's interesting because, of course, we depend on the predicate. If the predicate has side effects, so do we. But I would argue that even with a pure predicate, we're reading memory that's outside of our function scope, so that might change while we execute the function. Can we guarantee the lookup table? It's not a black and white issue in many cases. There's a lot of gray areas here. So while pure functions help us write safer code, there are different degrees of purity. And I take a very pragmatic approach to that. I try to make the functions as pure as is reasonable in the place where I want to use them. This typically improves safety at a reasonable cost. So back to our initial problem, we could say that the lambda is not pure because it captures outside state using this lambda capture with reference. And we can improve that by capturing by value. Is it really pure now? I actually don't care. It solves our problem. So in the example so far, our functions did not have to handle errors or communicate failure in any way. And that was, of course, to keep the example simple. Error handling omitted. Now in production code, things look quite different. We have to handle failure and errors. And if you don't want to use exceptions, at least in some parts of your code, for whatever reasons, you need other options. So here I contrast a classic version returning a bool to indicate success with std optional. And the example is this. I have a database or a storage structure, it doesn't matter in detail, and it contains very different kinds of data. Trends, images, tables. And looking more closely at the table, we can identify columns by key or index, and we can do the same with rows, which gives us access to a cell. And now we can ask, is there a number in that cell? And if there is, we can check if it's negative. So here is what we want. We want to find out if a value inside a table cell is negative. What could possibly go wrong? Well, the key into the database could be invalid. It might not be a table. Row or column could be out of bounds. The value might not be a number. And then we have one operation which does not fail, at least not for the type that I used here. So how would you do that in a classic fashion? I start with a function called getElement. I pass in a database handle and a key, and I receive by reference as last parameter my element. And a bool return flag telling me if the function succeeded or not. I've seen these a lot in old code and I hate them. They don't compose. But yeah, that's what we have. Get table, similar. It should extract the table from the element. If it's a table, again, the return value is if it succeeded. And the same for the cell. Here we need a location, so it's an additional parameter. And get numeric cell value, which should return as an int if it is a numeric type. Does anybody have a flashback here? We've seen this code before. So what happens? We create a C element on the stack and ask getElement nicely to fill it for us. And then we check, and if it fails, we exit ourselves, indicating failure. And then we do the same with the table, create on the stack, ask getTable to fill it, early exit on failure. And with the cell, and with the numeric value. And then finally, we can check if it's negative and return with success. Who has code similar to this? Yeah, a few people. So how would we do that in a more declarative monadic way? We change the interfaces. So the functions no longer return bool, but instead combine the output type into an optional. Now, if a function fails, we return an empty optional, and this indicates failure. And if it succeeds, we return the value wrapped in an optional. And we do the same for getTable, getCell, and getNumeric cell value. And for the sake of completeness, I also added a function that checks if a value is negative. Of course, not strictly necessary. But the interesting part is here I do not return an optional of bool because this function cannot fail by itself. And that's important because you will see in a few slides. So now we start a chain with getElement. And as mentioned, getElement now returns an optional of CElement. So what we can do now is we can call the function endThen on optional, and it will execute our function conditionally. That is, it will execute only if the optional holds a value. So we pass in the next transformation function, and it will be called or not called depending if the optional holds a value. Since we are working with values that may be there, this is called the maybe monad. So let's assume that getElement and getTable were okay, so we have a table. That an optional that contains a valid table. Now quiz time. We haven't seen any join here. Why do I still call this a monad? Is there some unwrapping going on? And let me just remind you of what the function interfaces are. Does someone have an idea? Yeah? Yeah, quite. As we can see here, the output of the first function is an optional of CElement, but the next function only accepts an element. We have done the unwrapping like a good monad should. Now, how would it does basically the join and transform in one step. Now, what would you do if we only wanted to join? So, for example, we have an optional of int, and we want to unwrap it. How could we do that? And there's no join function optional by any name. Does anybody have a suggestion? And I'll give you a hint. Yeah, okay, I think I've almost uncovered it because you can short-circuit the transform part by using state identity. It will still do the unwrapping first, and then it will do nothing with the result because it just passes through. And maybe I would not use that in production code, but it's pretty nice to illustrate the guarantees. Okay, back to our code. We pass the table, and here we need a second argument because getCell needs a location, so we wrap it in a lambda, pass it by lambda capture. And assume it was a bad location, so our optional is now empty. Because of that, the next call to endThen will bypass our next function. The optional will still be an optional of int, but it will be just as empty as the input was. Now, is negative does not return an optional, it just returns a bool. So here we use transform, much like in ranges views, instead of endThen. Use endThen if the function returns an optional and use transform if it does not. So what can you do with optional? Basic operations, you can check if it holds a value, and if it does, you can access the value. If you try that without checking, you get an exception. And you can simplify by moving it into the moving the assignment into the if statement. Then you check directly. Or if you don't care if whether it held a value or not, you just want to fall back to a default, you can use value or. Now, comparison. Who likes the code on top more? I don't see many hands. Who likes the code on bottom more? Some undecided, but the majority clearly. So how about logging or something like that? I mean, okay, it won't misbehave, but we might want to log failure. There's a function called sibling to end then. It's called or else, and it will only call the function if the option is empty. And since empty is our indication of failure, we can catch failure that way. And why is it a template function? Because it needs to return an option of the correct type, and it cannot know what that type should be, so I tell it via template parameter. Now, there's a problem here, because if, for example, getCell failed, I can catch the fact that something failed, but I don't know where it failed, I don't know what failed, I have zero error context. This is not good enough. Enter still expected. A new type in C++23, which is very similar to optional. Instead of optional, we return still expected. And it has a second template argument. The first one is the value, just like with optional, and the second one is error information. Now, if a function fails, it does not return empty anymore, it returns an unexpected, which is a custom error type that you can choose. And for example, my C error type, it accepts a message in the constructor, and it could also capture the call stack in the constructor using the stack trace library. You will find it in my references if you're interested. If it's okay, we just return the value as before, wrapped in an expected now. The chain of operations is identical and then works the same way. So it calls the function if expected holds the value type. If something goes wrong, we switch to the error type, and from there on, and then we'll bypass any functions, and the error state is preserved. At the end, we can capture the error state in or else, and yeah, do something with it. So what can we do? We get it passed as parameter into our log function. So if getCell fails, it captures some error information that gets passed down to my log function, and now I can do some useful logging. The function also returns an expected, so I can choose what I want to do. Do I just pass through the expected unchanged? Do I amend error context? Or maybe I just fall back to a valid value. That's an option. I just wouldn't do that in a function called log. That might be surprising. Usage is very similar to optional. You check for the value. You can access the value. Now you can alternatively access the error. And expected always holds either value or error. Again, you can move the assignment into the if statement if you want to check right away. And again, you can use value or if you want to fall back to a default value. Error or exists as well for special use cases. Now, if you have a fragmented code base or maybe use libraries that return expecteds, you might get different error types. And expected allows you to transform these error types. So let's say I have an expected with C error, and I need my error so I can pass it on to my next function. What you do is you write a conversion function that accepts C error and returns my error. And then you call transform error on that using that function. If the expected contains an error, it will be converted. If it does not, only the type changes, but no values change. Now, we've seen how you can use optional and expected to check if every function in a pipeline succeeds. But sometimes we want the exact opposite. We want to call one function after the other until the first one succeeds, and then we want to run with the result. And that's easy to do with optional. Here, I want to start an application, and I want to decide what UI language I want to use. And I have given the user some options to choose that. Command line, registry or a similar system, environment variable. And I have a fallback in case nothing was chosen. And here's the pipeline using std optional. in this pipeline, the first function that returns a value wins. So let's assume that getLanguage from command line failed. We have an empty optional. Because of that, or else we'll call the next function. And let's say getLanguage from registry succeeded, so we now hold the value. And because of that, the next function gets bypassed, our optional stays the same. Had we been left with an empty optional at this point, our value OR would have kicked in and provided the default value. Now, some of you might have noticed that I put monad in quotes in this section. Does anybody have an idea why that could be? Yes, please. I'm not flattening, yes. Yeah. I would go one step deeper and look first at the functor side, because our functor dimension is that we are able to transform optional of A to optional of B to optional of C. We can transform the types and the values. The monad dimension is that we can unwrap, like you said. So optional of A to just optional of A. And as we have seen, the optional typically does not give us the separate function for that. It goes diagonally across this table with and then. Now, what does this have to do with or else? Nothing, because we are stuck at the value type of the first function and nothing changes there. We are not moving across this table at all. This is not a monad. I would maybe call it a monadic style operation, but it's useful, so I included it in the talk. One of the first things you will encounter are compiler errors that you're maybe not used to. That's typically the first obstacle. And you spend, after you know a bit, you spend a little more time on compiler errors, but you spend less time on runtime errors, which I think is a good trade-off. Still, I don't love fixing compiler errors, so I wrote myself a little cheat sheet, and I would like to share that with you. So let's say we have this pipeline and it does not compile. And what do I get? I get something like this. The dreaded wall of text. MSVC, but the other compilers are not that much better in this regard. However, look at the beginning, look at the end. There, usually you find the initially useful information. For example, in the beginning, I find that I cannot find a match and call operator or something, and then at the end that some template argument could not be deduced. And in the beginning, that's similar to what Clang and GCC will tell you. So how do we fix that? I go through my checklist, and the first step is that I want to know in which stage of my pipeline does the error actually happen. And if you cannot determine that easily, start splitting up the pipeline until you can really pinpoint where the error happens. Now that you know in which stage the error happens, check are you using an overloaded function maybe? If so, wrap it in a lambda. And this, by the way, is the error that we have seen. Then, does the function accept the correct type? And for example, for lambdas, it's sometimes really useful to replace auto with the concrete types, if that's possible, that you want to use. Helps the compiler help you. And the same goes for the return type. If you can't explicitly spell out the return type, the compiler will love you and you will love it back. For stud ranges view specifically, you might sometimes miscount the number of joins you need. So you expect a vector of thing, but you get thing or vice versa. And sometimes you are tempted to use views const, maybe even in generic functions. Don't. Sometimes it will work and sometimes it will break with weird compiler errors that you cannot decipher. Just don't use views by const. If it's a generic function, the typical way is to use a forwarding reference. If you know it's cheap to copy because it doesn't own data, you can use it by value. I cannot really go deep into this topic, unfortunately. It's a talk on its own. Yes. And finally, for optional expected, so you could mix up the and then and the transform, and then it returns thing, but it should return optional of thing or vice versa. So in my experience, these are the typical initial compiler errors that you get, and now you know how to fix them quickly. So we have seen the monadic operations of the standard library. But let's leave this comfortable path and write our own. And there's something very similar to optional in the standard, to optional in the language. That's a pointer. Can be null, can be valid. Let's write the pointer monad. And I want to reuse the example from optional. So the goal is to get the information where that table cell value is negative. And when you look at the functions from the pipeline in the classic version, we changed them to return pointers. You might notice it looks very similar to optional. Of course, we have to change our implementations as well. And it looks something like this to fit on a slide. Not a fan of the style, but it fits. We check in each if statement, we check if the pointer is valid before we go further. And the whole function returns a value. So I return an option because a pointer to bool doesn't make sense to me. And this is how it would look with the custom pointer monad. So here is the sequence. The first function returns a pointer and gets wrapped into a monadic wrapper called cptr. Like optional, it has a function and then I decided to use the same name, which follows the same logic. If the pointer is valid, it calls the function. If the pointer is invalid, it bypasses it. So the next function also returns a pointer, valid or null pointer, and the same for the cell and for the numeric value of the cell. And now it gets interesting because I don't have implemented any transform in my interface. Why does this work? Because actually we have transitioned seamlessly from my pointer monad to standard optionals monad. Because get numeric value, the integer is also an optional of int. And then we can do a transform on that and get our result. So how is it implemented? It's a template class. And it should only handle pointers. So I restrict the template to only handle pointer types using C++20 concepts. Now some boilerplate. I have a default constructor that creates a null pointer object. And I have a custom constructor where I can directly pass my an existing pointer. And then I have some helper functions that mimic pointer-like behavior. That's just a basic set. I could add more than that. But the fun is in the monadic function and then. So we want to pass a callable, a function or a function object or whatever, into it. And the return type we have to deduce because it depends on what the function returns. In the implementation, we start with the template arguments. tptr is the pointer type that we currently hold in our class. So it's a class template argument. And tcall is the function template argument, the callable that we want to execute if our pointer is valid. Inside, I prepared two helper types. The first, tref, is the reference type, the matching reference type to the pointer type. And tret is the return type of the function, which gets a reference now and not a pointer. So the function itself does not need to check the pointer if it's null. Then we have two branches. The first branch is for callables with which return pointers. So we check our own pointer. If it's valid, we invoke the callable. So we forward the callable and our dereference pointer. And then we wrap the return pointer into cptr, so the next stage of the pipeline can immediately call and then again. If the pointer is invalid, I return a null pointer version of my wrapper of the correct type. And then I have a second branch, which handles return types that are not pointers. And for now, I only accept the optional. And this is the check I use to see if it's really a stood option to anything. I don't care what's inside the option, I just want to have the wrapper. Now, I invoke again if the pointer is valid. And this time I return without wrapping because it's an optional, it has the monadic interface. Or I return an empty optional of the correct type. Here I highlighted these differences, wrap pointers into CPTR and leave non-pointers as they are. And of course, I could consider other cases, but for now I just added a static assert, so if somebody passes me a funny looking callable, I will give them a reasonable compiler error. And this is, again, how to use them. So, of course, there's lots we could add. We could add transform. We could add support for functions that already return CPTRs, whatever. I still hope I could illustrate the basic idea of creating a monadic wrapper, because I think it's not really magic to write something like that. I mean, of course, it's template code, so you might look to sign up for Walter's workshop, but it's not that much code even. Okay, monadic operations are useful on their own, but you can do more. You can combine them. In this section, I want to show you two more things, two more monads. Very briefly, I will just go over them conceptually this late in the talk, and then how you can combine them. Again, we have a pipeline, and the task is really slow, like really slow. We certainly don't want to block on that. So what's an alternative? We can use a continuation monad. Here, we create a future which is available almost instantaneously, and the actual computation is moved to a thread and happens inside the future. Now, once the value inside the first future is ready, a continuation can be triggered that starts computing the second future. And again, monad magic is in play because the functions I use don't need to know about the future. They are just the functions that transform the values, and the unwrapping is done for them. The only requirement is the functions need to be thread safe. Since my functions are pure, I'm good on that. And there is going to be a continuation monad in C++26, but not existing right now in production use case. So I wanted to show something that you can use if you want to. And Qt is the most stable library that I know of that contains continuation monad. So I use that. You can use it from C++17. So what do? We start the pipeline by calling Qt concurrent run. And here we need to pass first the function that should be our initial computation, do our initial computation and the initial value. We continue with then, similar to the end then. So we attach the next function that should be computed as soon as the first future is ready. And we get the final future as our return type. And we can do many things with it. We can query it, we can cancel it. Here I just wait on blocking until it's done. But what if I want to do tracing and maybe I have multiple of these pipelines running in parallel and I don't want to mix them, but I also don't want to use a global mutex for that? How could I do that? Well, let's look at the second monad, the writer monad. It makes tracing part of the call chain. How does that work? Here we construct the writer object, which is a wrapper around our value. And again, of course, it's a template, so it can contain any type of value. When we call our function, we can now pass a second argument containing trace information. And as you see, the value is transformed, but the trace information is also collected in the wrapper. And the same goes for the next stage of the pipeline. And when we're done, we can both get the result from the writer and get the trace information and loop over it, look at it, whatever we want. Now, this is maybe of limited use. It's much more useful if the functions themselves return detailed trace information by returning basically a pair of result and trace information, because this way you can trace input parameters, intermediates, outputs, whatever you like. And the pipeline does not need to take the trace information anymore. You can mix, in my implementation, you can mix both styles as you like. Yeah, and then I'd like to combine that with a continuation monad. I need a little glue now. The first part of glue is a simple function that creates writer object, make writer. Nothing special about it. And we accept an initial value. So it constructs and returns a CWriter object around that initial value. Then now needs an interface that understands the CWriter wrapper, and my functions don't know about CWriter. So I have added a wrapper called addWriterAPI, which will turn it into a function that can handle the CWriter. And we do the same for the last stage. And the result is a CWriter string, the string being our result. And again, I can loop over the trace information and do something with it. So on the one hand, you have the continuation monad, which allows you to easily offload tasks into threads. On the other side, you have the writer monad, which allows lock-free tracing. And when you combine them, you get lock-free per pipeline tracing concurrently. Of course, you can also use the writer monad in other monads with expected optional ranges views if you want to know exactly what's happening inside your pipeline. Okay, now I come to the extensive part of the talk, because it took me a while to get the numbers and I have less than 5 minutes to present them, which means I cannot explain my approach in detail. You will have to trust me. Okay, no, of course you can't trust me. We're talking about benchmarks and there are so many variables to consider. If you really care about performance, you have to test yourself, your use case on your hardware. But still, I have some useful findings I'd like to share. So remember split ranges views. Let's see how they hold up against raw loops. And my test scenario was this. I start with a small range, 50 items. Within 3 iterations, I blow it up to an intermediate range of 250,000 items approximately. And then I calculate it down and accumulate it into one single result. Single-threaded everything, no multi-threading involved. And now I have different options to do that. I can do the basic thing and do nested loops that directly work on the initial input and directly give me the final output. I can use views to create a view on this intermediate large vector and then compute it down to one single result. I can do the same in a classic fashion by creating a vector that holds the intermediate values. Or I can use a view to create this intermediate vector. Now, the integrated is the baseline. And when I use the ranges views, it's about 2 to 13 times lower. I should note there's no extra work going on that would hide these effects. But it's still faster than a classic loop with vector, quite a lot faster. However, if you know the size approximately in advance, you can pre-allocate, and then it's about equally fast as split ranges views directly. Combining views with vector is, as expected, slowest. 38 times slower sounds bad. How bad is it really? Well, on my not super fast computer with these 250,000 items per item, in the worst option, I spend a bit more than 6 nanoseconds per item, which I think is probably too much for a data center or something where you crunch numbers, but might be reasonable for an UI application that has to wait for user input anyway. So depends on your use case, I would say. But why should we not always choose the fastest option? Because separation of concerns. The fastest option is handcrafted and does this job and this job only. All the other options give you some way to separate them out into different building blocks that you might be able to reuse again. It's a trade-off you have to choose. Now, how about the error handling? In my example, I have 5 gates, and the value has to pass through these 5 gates, and each gate can either accept or reject the value. And they are implemented in different ways. So we have a classic bool flag, we have optional, expected, and exceptions. Now, to make it a little more real world, I simulated a little work before entering the first gate by making a lookup in a 10,000 item unordered map. And I also used different rejection rates. Now, because in the all happy path, all of these are approximately equal, approximately. If I add some sad or all sad path, then bool, the classic bool is the clear winner, and optional expected falls behind a bit. Exceptions are really bad, but this might be Windows special. Okay, to summarize, if you want fast, then you go for classic manual implementation, implement your special problem in the special way that's best. However, you can get much nicer code for a reasonable price if you are not in the hot path of your application, which means you need to know what your hot path is. And if you understand that, you can decide what's the trade-off worth, is it worth it to make the specific optimization. So we're coming to the end. What does this mean? Where does this leave us? What does it mean to you in practice? I have 3 takeaways, but how strongly they apply to you depends on your experience, what you code, how you code, with whom you code, for whom you code. You have to pick and choose for yourself. The first takeaway is that monadic operations, but generally functors and monads, are useful concepts to know about. We have seen how functors help us lift out common repetitive code, separating the what I do from where I apply it. So I can write a piece of code once and then apply it to different things like single items, optionals, vectors, and so on. Monads give us the power, give us additional power when we want to build pipelines that we cannot build with functors alone, because they give us the ability to do unwrapping. I hope I have given you a taste on how useful these might be for you, but it's just a start. If you look at some of the references behind the link I'll share in a moment, you will find out how much more you can do with them. As a second takeaway, I would argue that pure functions are good for your code health. They make it safer and easier to test, and this applies beyond functors and monads. So even if you decide after this talk that functors and monads are not really for me, maybe take this one to heart. And finally, the monadic operations in C++23 are immediately useful in some common concrete use cases. And you don't need deep understanding of the theory behind functors and monads to make use of them. Try them out, see if they fit your use case. Just a word of caution, don't rip out existing tested and validated pipelines. Keep them as they are, but if you want to write something new, try out if maybe the monadic or way is a better fit for you. Let's recap what those pipelines were. The ranges view monad, if you have a pipeline where each input produces n outputs. Optionals may be monad if you want to build a pipeline where some or all of the functions might fail. Alternative listed expected if you want to provide useful error information in case of failure. And optionals default monad if you want to grab the first usable result from a list of functions. These will help you write safe and readable code, the monadic operations in C++23.